Uh-oh, here we go. Back to the 80s today, folks. Back to the 80s. It's our 80s Chapter 2 Science Review video. We're starting off here with the doctor, the myth, the man, the myth, the legend, Dr. Phillips. Here we go. He's going to talk about density. All right, Doc, it's all you, brother.
Hello, folks. Today we're going to talk about density. Density has a formula. Density equals mass over volume. And that's a kind of neat formula because the formula tells you what the definition is. Density is the amount of mass per unit volume of something. Now it's time for you to change your thinking. It used to be that you would say that something was heavy or light. But what you often meant was that it was more dense or less dense than something you were comparing it to. For instance, a small piece of styrofoam is light and not very dense. But a huge room full of styrofoam would be very heavy, but it still wouldn't be very dense. The density of a substance doesn't change with the amount of that substance that you have. That's why it's a specific property. We can use it to identify types of matter.
So like you're saying, when I see that D equals M over V formula up there, right?
Yep.
So if I have one specific type of substance, if we have more mass, you're telling me it's going to be a fixed ratio?
It will still be a bigger volume if you add more mass. For instance, aluminum has a density of 2.70 grams per cubic centimeter. Grams is the mass, cubic centimeters is the volume. It doesn't matter whether you have a little piece of aluminum or a huge piece of aluminum, the density will still be 2.70 grams per cubic centimeter.
Yeah, because when you add more mass, isn't it going to take up more space more than likely?
Sure, the ratio is the same.
The kids always mess that up. Oh, good one. All right, keep going.
Now, we can also, if we know the density of something and we know its volume, we can solve for its mass. We can also, if we have the mass and the density, solve for its volume. So the magic triangle here might help you with that. Mass equals density times volume. Density equals mass divided by volume. And volume equals mass divided by density. So if you're having trouble with moving the components around, use the magic triangle. It will get you there.
And let me just comment on that. That triangle is huge. But here's the thing, guys. The triangle's really going to screw you up if you don't put the letters in the right spot. So please, look at that. Woo! Look at it.
Whenever you have the magic triangle, a formula in this arrangement, this one goes on top.
You got it.
The top one goes on top.
You got it. That is so important. Excellent. Good stuff.
Now,
all right. Oh, we're going over here?
Let's apply.
You know what? I think your desk is almost as messy as mine. That's quite impressive, Dr. Phillips. Hold on. Look at that. Oh, man. Look at that. No, I think I'm a little messier, but I'm impressed, man. I'll tell you. Here we go. Oh, there you are.
All right.
Now, well, wait a second. Wait a second. Wait a second. We're celebrating the 80s. You know, and I know with the 80s we want to revert back. Like, let me ask you, Dr. Phillips, you know, what did you look like back in the 80s? I'm just curious. Like, you know.
I had lamb chops down to about here.
No, you didn't.
For a while I had a beard, and my hair was like halfway down over my ears.
So you kind of look different now, but you're still Dr. Phillips, though, right?
That's right.
Can you kind of revert back to your old ways, and can we try this wig on you since we're celebrating?
This might be a little extreme.
Oh yeah. Let's back to the 80s.
Some physical changes are extreme.
Look at that. Wait a minute, now ask yourself the question. Hold on. Dude, that wig is awesome. Now wait a second. Before we move on, dude, wouldn't it be awesome if we could quick dye your mustache too? That's all.
No.
But no.
Keeping that the way it is.
Yeah. But now, do we still have Dr. Phillips? This is just Dr. Phillips with a mullet wig. So this is a physical change. He looks different, but it's still our good old friend, Dr. Phillips. All right, awesome. All right, go ahead with your demo.
All right. Now,
this mullet's great. Go ahead.
We can find the density of different substances in different ways. Here we have a brick. Now the brick, you would say, was heavy, but really what we mean is that for the amount of volume it takes up, the amount of space, there's a lot of mass there. We use a triple beam balance to get mass. We do not use a spring scale. Spring scales give us weight, and we want mass per unit volume. Here we have a piece of lead. Lead is thought to be very dense. It's not a lot dense compared to, say, gold or uranium or iridium or osmium, which have much higher densities.
You know what? Hold on one second. Let me get around here so we can kind of see that on here. Sorry guys, I'm not really good with the camera. All right, go ahead, I'm sorry. Here, now we can see it good.
So when we find density, we need to take a couple of steps. We have to get the mass and the volume. Putting an object on a triple beam balance, getting its mass, is the way to get that quantity. And remember, you know how to do the sliders on the balance to get the right reading. Now that takes care of mass in grams. Now we can find its volume if it were a regular rectangle by doing length times width times height. But this is not regular. So we need to find its volume by displacement.
Mr. Racich, please contact the office. Mr. Racich, contact
Live, this is live television, folks. Doesn't get any more real than this. Go ahead.
So to find the volume, if it were able to fit in a graduated cylinder, we could fill the graduated cylinder up maybe halfway, carefully immerse this in the water after taking its volume, and then take the volume again. And the difference between those two volumes is the volume of this.
So,
just like if you get into the bathtub and the bathtub's halfway full, the bathtub goes up.
The water level in the bathtub, yeah.
Equal to your volume, as long as you go underwater.
That's why they call it displacement. Like when an object goes in, it like displaces and moves aside the water because you're taking up space. You know what's so cool about this? This was also from last chapter, so I guess the stuff we learned in chapter 1, obviously we learn it then to help us build to understand density right now. Oh, very important. Go ahead.
And it will continue to do so. Now, so you can find the volume by displacement or by measurement depending on whether it's a regular shaped solid or whether it's an irregular solid. Now sometimes we want to find the density of a liquid. Now to find the density of a liquid, you first find the mass of the container in which the liquid is placed without the liquid. Then we pour our liquid, this is ethylene glycol, which is antifreeze from a car, and then you subtract the mass of the container itself from the mass of the container plus the liquid, and that gives you how much liquid you have. Then you read its volume, and there you're back to using the formula. Now, of what use is this formula? Well, once you find the density of something, one of the things it tells you is, will that object sink or float in water? Water is a unique substance. 1 gram of water has a volume of 1 milliliter. So its density is 1 gram per milliliter. So anything that's more dense than that is going to sink. Anything that's less dense than that is going to float. But you say, wait a second. There are some things like fish or submarines that stay at their place in the water and they don't sink or float. That's because they adjust their density by altering the amount of air in them so that you have what's called neutral buoyancy.
Oh, I like that.
It's not floating, it's not sinking, it's neutral.
Nice.
Now,
Excellent.
does that apply to people? Yeah, it does. People with a little extra fat on their bodies are less dense than water and they float easily. They bob like a cork maybe. Heavily muscled males who have been doing a lot of weightlifting and not having a lot of fat on their bodies.
That's definitely not me.
I don't see any of those here.
Yeah.
They may have trouble floating at all. They have to stroke all the time they're in the water just to stay afloat because muscle is more dense, and that's the most dense tissue in the body, so lots of muscle takes you down.
Awesome. Cool. Perfect. That's some good demos there. Look at that. So again, density depends on mass and volume, and that is a good thing you brought up about, these are one of those awesome definitions where it's the formula. And that formula triangle, please don't forget that, guys. That'll help you solve the problems. Please put the letters in the right spot. DMV, okay? And then we looked over here. Dr. Phillips reviewed liquid displacement with the graduated cylinder, talked about the mass of this little weight right here, and the block. You got one more thing for us? We got about 30 seconds left. This is all,
Here's
what is
something
that?
For you to figure out. This is a regular egg out of my refrigerator. I have not done anything to the egg.
Okay.
Normally, an egg should sink in fresh water. If you put an egg in a pot of water on your stove and it floats, throw it out. It's no good. But it should sink. Now, what's happened to this egg? I have messed with the system, but not the egg. See if you can figure out why the egg appears to be neutrally buoyant when it's not.
Oh, we should discuss that in class tomorrow. Okay, very good. So take a look at that egg. Okay, we will discuss that in class tomorrow. Oh, cool, excellent. All right, I think we're just about done.
Going to try was solubility. I had
Okay.
some. I
Is
had
that-
some sand before, and I wasn't sure. I have a container here, and I can't
Timmy
remember.
Mulray, if you're in the building, please come to the office or contact the office. Timmy Mulray, if you're in the building, please come to the office or contact the office.
Okay,
I,
go
I
ahead.
couldn't remember if this was sand or salt, but then I remembered that sand doesn't dissolve, but salt does.
So solubility, like you kind of sounds like dissolve, you know what I
It
mean?
can dissolve.
So like solubility, ability to dissolve, is that kind of like what it means? Like different substances can or have the ability to dissolve?
There we go.
Yeah, see how
So
those
get
words
that.
work together there? So that's a property of substances.
So I was going to try and combine that along with the idea, and I also know that salt water conducts electricity, but regular water doesn't.
So this is getting into section 2.3. Oh,
Yes.
good stuff. All right.
Okay, and so we're going to look, I have a little electrical tester here
Mm-hmm.
where I can test the conductivity. All right, so
Ah.
I have a paper clip here, and if it does conduct electricity, it will complete the
Well-
circuit.
So you're
Okay.
so you're telling me that metal paperclip right there, that metal has properties where electricity can carry through it.
Carry right through and complete the circuit
Ah.
and get the light on.
So this is in section 2.3. That's like a
These
property.
were a magical time.
All
Uh-oh.
right.
Hold on one second. I think that's
A
Mr.
magical
Sick.
time.
Yes, the
Wild
80s were.
hair, outfits.
I guess he knows we're filming. Hold
It
on.
was relevant for the first and only time.
Don't go there. Don't go
Not
there.
as relevant as the 1986 Penn State National Champions.
Does that national championship still
Hope the science
exist?
video's going well.
It's going. I wish you'd leave us alone.
Have a good night.
Thank you. You too. Does that national championship still exist? I thought they took that off the record books, but never mind. Okay, go ahead. So wait a second. So that metal can conduct heat and electricity. Some substances don't.
Right.
Okay,
So
cool.
one of the properties is conductivity. Surprisingly, when salt is dissolved, it releases electrons into the water and it conducts electricity and light the bulb.
Okay.
But this is just water, all right? So there is no conductivity there.
So hold on one second. Let me rephrase. This is important. So you're telling me metal could, electricity could travel through metal to get that light bulb on.
Absolutely.
Whereas now we're trying to put electricity go through water to get that light bulb on, and it won't. So water's properties, it cannot conduct electricity.
Right.
But metal, yes. Oh,
right.
cool.
So now, to see if this is white sand or salt,
Uh-huh.
I'm going to mix it into the water that doesn't currently conduct electricity, see if this dissolves.
Solubility, ability
Okay.
to dissolve.
We're going to put that
Solubility.
in there and stir a little bit.
Dude, I could just
Okay.
stare at that, man. That looks like an ice cube in there, but it's not.
We're going
Because
to
it
put
would
that
float.
in there, and now if it has dissolved, it'll release its electrons into the water, and
What the heck?
all of a sudden, we now have conductivity.
Oh.
So we've proven that this isn't sand, this is salt, it does dissolve, it has solubility, and it conducts electricity.
So salt water isn't the same as water, so therefore it's got different properties
Different
than
properties.
pure water. Oh, look
Different
at that.
electrical property.
Cool.
Now,
This is actually really good, Mr. Deback. Let me give you
and
credit.
now we're going to take, I've got a white powder here, sort of generic powder, and I'm going to add iron filings. I'm going to put some iron filings in here.
And is that
and-
like powdery metal?
This is all powdered down very, very finely. I'm going to take it and mix these two together. And one of the things you can do, and it takes a while to get it just right, is you can separate different types of material by their properties.
Can I separate it by hand maybe? Or do you think
Well,
that'll take
the
a while?
little pieces are so small
Yeah.
that even with tweezers
Look at
you
that.
couldn't grab them.
Okay.
But I know that iron has a magnetic property. And so
Oh.
by taking a magnet and taking it and stirring it into the material and shaking it, I
Look
can
at that.
remove a lot of, I'd have to do this repeatedly,
Sure.
but look at all the iron that's come off onto that magnet.
So that's a way to separate a mixture.
So there's a way to separate
Look at that.
do that.
Awesome. Look at look at that. Looks like a
It's really, it comes out, it's surprising.
That's really cool. Excellent.
I
We got
love-
time for about one more.
Just real quickly,
Yeah.
we have oil and we have water. There are two different ways to cook, but if you would put each one over heat and you put a thermometer in there, you could see what the heating properties were of either one. They're very different. You'd be surprised, and we'll do this in class later. You would think all liquids may increase and decrease in heat at the same time, but actually each different compound or substance has unique characteristics. So we'll leave that be a bit of a mystery as to which one heats up and cools down quicker than the other.
Awesome. Great job. Anything? That's it.
There you are.
I'll
Okay,
tell
that's
you.
what I was working on.
Jack of all trades, master bike
Oh.
mechanic, master science teacher. We got, I got 30
One
more
more.
seconds.
Here you go. I
Look
wanted
at
to
you.
put
You
some
just can't
iron-
stop. You
iron-
can't resist this video.
I got some iron filings in water. Now, another
Ew.
way to separate that would be to take it and pour it through filter paper. You put it through filter paper.
Looks like
and-
my coffee in the morning.
Yeah, most of the water is going to go through the filter paper. It's a little bit chocolatey, but we're going to be left with, given enough time, we'll keep most of the metal up in the paper.
Awesome.
Okay, we'll take
Awesome.
that, and I can show you up here. It's taking a while for the water to go through. But we have a glob of metal here at the top.
Awesome.
Okay.
Cool. Perfect. And you can also boil liquids away if you need just the solid, if it's dissolved.
We could do that.
There you go. Well, thank you so much.
All right, come again.
Love it. Awesome. Thank you, Mr. Deback. Here we, I'm a classroom. Look at alumni wall. Look at all those college students. Look at all the success back here. Dude,
Okay.
what are you doing? What? Dude, wait a minute. Wait a minute. Who is this?
Yeah.
Who is this?
Science teacher of the 80s.
What? Wait a minute. Wait a minute. Wait a minute. Are you telling me that, wait, is that Miss Camilleri?
It is.
You look different, but you're still like the same person?
Sure.
So did you undergo an 80s physical change?
80s physical change right here.
Man, look at that. Are you just channeling your inner like Madonna or like, who else? Like Debbie Gibson, right?
Oh,
Right?
yeah.
Who was your favorite singer back in the day?
Oh,
Or we should say producer of sound energy. Cyndi Lauper.
Cindy Lauper.
Girls
Okay.
just wanna have fun.
Sure.
Nice,
sure.
nice. Now,
Dance to
I
that.
gotta pick up my kid in 15 minutes.
All
So
right,
we
so
ready to
you're
do some
ready?
demos?
Here we go.
Let's do it. Where am I going? Help me.
Oh, okay.
I'm filming.
You go first.
Oh, I'm
go
going
first.
first. Oh, all right. So go up to the front there.
All right.
Here we go. We're gonna transfer the camera.
Transfer off.
Gotta love our high quality skills here. Okay. Dump of the classroom. Here we go. As
Take my
always.
glasses off here. That was a great,
What do you think?
great 80s physical change.
I know you're a little older than me, Miss Camilleri. I was kind of a late 80s, 90s kind of a kid.
Uh-huh.
And, like, would you think that this kind of follows the form?
Sure.
And I peg my cuff my pants?
Yeah,
Hold
that's
on
a late
second.
80s.
Hold on.
Oh, nice. Nice.
Look at that. Is this like 80s
Yeah,
or what?
that's a
So-
late 80s
Late
outfit
80s
right there.
outfit. So what, I wish I still had a pair of Z Cavariccis. I really do. But even though I look different,
Right,
I'm still the same person.
yeah.
All right, so that's a physical change. All right, here we go. I guess I'm talking about solids. Oh, I'm getting old. Ouch. Solids, liquids, and gases. Okay, I'm going to keep this simple so we all understand it.
I think we do need to explain your 80s physical change haircut, though. This is not the norm.
Well, I got news for you. Went to the haircut place last night. And I usually get my 1 into my 3, you know, like that
Right.
faded in.
Yeah.
And I've always wanted to do this for years. I was going to go with a half a head.
Oh,
To
sure.
surprise you guys, but
Yeah.
I kind of want to go back tonight and get the rest done so I look
Yeah.
normal again.
Yeah.
So I just had to do it like this. So I guess this style was kind of in back then.
Oh, sure.
Yeah, what is this called? Like, I don't know what kind of haircut this is.
Oh,
This is
no.
not even know either.
I don't
But
know.
anyway, I look a little bit different,
Yeah,
but I'm still the same person. Miss
Same
Cameron
person.
told me I should get double polo shirt with
Right.
double pop the collar.
right.
But I'm
Pop
still
the
the crazy
collar.
science teacher.
We really want an alligator on that shirt, but we'll take the
Dude,
polo.
It's not real
okay.
polo, it's at the outlets. It ain't
Oh,
the
there
real
you
polo.
go.
It's cheap. Oh, I'm cheap. Are you kidding me? So again, I wish I had the alligator, but
Hey, that's all right.
there you go. You know, here you go. In 1986, I was in 3rd grade.
Oh,
Miss Cameron.
no.
Miss Cameron, where were you in 1986?
I graduated in 1980s.
Graduated where? High school?
High school.
Nice. Very good, very good.
And you
So,
were what, in 3rd grade?
I was in 3rd grade, yes. What do you think
You
I
were
was like
8.
as a 3rd grader? What do you think I was like as a 3rd grader?
Oh, I bet you were running around like crazy.
No, totally not. Totally.
Really?
Totally. Come, look at me.
Did you follow all the rules and everything?
Kind of.
Yeah, good.
Here we go.
All right.
Solid. Okay, solid, liquids, and gases. Okay, all forms of matter. One thing you need to understand is this. Solid, from last chapter, vibrate in place, packed tight together. But again, everyone forgets with solids. They think, ooh, frozen, not moving. Wrong! Solids vibrate in place. All matter has molecules that move at different rates. Okay? So solids packed tight together, vibrate in place. As we add heat energy, we begin to melt. And that critical temperature at which we melt is called the melting point. Okay, and you're familiar with the melting point of water being 0 Celsius or 32 Fahrenheit. We melt into a liquid, and we go from a solid to a liquid. And how do liquid molecules move? Not like this, not vibrating in place. They got a little more energy. Oh, heat energy. Energy comes in. And these guys, when they get that little bit of heat, right, they start to move around a little more and a little more. And they kind of skip past each other, but they're still kind of close. But they kind of skip past, they kind of flow. You know what I mean? They kind of flow. Was there like rap back in the 80s? Where you like freestyle and flow and stuff? Or was that more of a 90s thing?
I think that's more 90s.
Oh, okay. There you go.
Yeah.
But still.
No, Ice. Ice Baby.
Or is that 91?
Oh, I don't know.
Ice Baby! Oh,
Yeah.
solid. Go
There you
figure.
go.
Very so can relate everything. Okay, so we start to melt with more heat, and all of a sudden the molecules spread out because of the added energy, right? They now move around and they act as a liquid. But let's say we add more heat, and more heat, and more heat, and more heat, and more heat. Now I'm adding a lot more heat. More heat, more heat. A little bit over here, but look at how much over here. More heat, more heat. The reason why is it's going to take a lot of heat to go from a liquid where they're kind of just flowing and skipping past each other, you know, woohoo, to whoo, nuts, gas, raw, spread apart and crazy. So we call that process vaporization. And again, it's added heat, liquid to a gas, vaporization. Now look at that word vapor. Vapor means gasization. I guess it means process. So we call it gasization. Liquid to gas. A lot of heat is needed to make that big change from like liquids where they kind of just flow and stuff, right? To, whoa, gases all over the place, okay? So it's a big difference. We're going to come back to that in a second. There's two types of vaporization. But let's do the opposite, gas to liquid. So we're going to go from, whoa, crazy to flow. Well, what causes those molecules to act like that? The heat doesn't enter. Instead, the heat, physical change. My chalk just broke, it's still chalk. The heat leaves. The heat leaves the substance, and when there's no heat, they start to not have as much energy. And instead of going crazy, they start to kind of, oh boy, get back together again, and they condense. C-O-N-D-E-N-S, sation. Condensation. Oh, wait till you see Miss Cassavage. Condensation. We go from a gas to a liquid. And the liquids are just flowing. They were like this because they're the same substance. but now they're like this because energy has left. They've cooled down. They kind of like chilled out, you know, okay? And then let's say more energy leaves, more heat energy, more heat energy. Instead of just flowing, they start to just kind of vibrate in place. Well, why did they slow down? Because the energy left, and that process is called freezing. Okay, so as we go from solid to liquid to gas, we gain heat, thermal energy. Gas to liquid to solid, it leaves. There's a certain song that we love to sing, but I'm not giving that away. Ask your teacher to sing it if they haven't already. Okay, so that's the general process. Now, two things I want to hit. Difference between boiling and evaporation. And I want to tell you something. When you have a phase change, it's always a physical change. Because you remember, I kept saying, molecules as a solid packed tight together. Well, each individual block, each molecule, no matter what it is, when you heat them up or cool them down, they're only pulling away or moving closer together. They're not like breaking apart to form something else. So I will give, this is my free Perseus saying, I'll put it online. Any phase change is a physical change, okay? Because the substance stays who it is. Oh, I stay who I am. But they act differently, they look different. Okay, boiling and evaporation, real quick. Can we do it over here?
Yeah.
Okay, so there are two types of vaporization. Here's a pot of water, okay? Here's water. I'm going to show boiling real quick because I got about 1 minute left. Okay? We had fire down here for water at 212 Fahrenheit or 100 Celsius. All of a sudden you start to see these little bubbles forming all throughout. These bubbles are gases and they float upwards because they rise. And what happens is each of these bubbles is a liquid to gas transformation, and they float right out. Okay? Because they're converting from liquid to gas, they're floating right out and rising because they're hitting that critical temperature, that boiling point. Okay? Water boils at 100 Celsius or 212 Fahrenheit. At 213, this can't exist. These molecules become a gas. Okay? So boiling occurs all throughout at one specific temperature. In page 15 of your packet, please fill that out or have your teacher go over that. It's a really good diagram that covers a lot of this. Evaporation, which is another example of liquid to gas. Let's do another pot of water again. Instead of liquid to gas bubbles all throughout, they tend to just occur at the surface randomly. And over a wide range of temperatures, they escape, escape, go, escape, up, escape. And eventually, the liquid level decreases and drops over time. But here's the one cool thing. They both are liquid to gas. They both are forms of vaporization. They both involve an influx or a gain of energy. But evaporation only occurs at the surface, boiling throughout. Evaporation can happen at many different temperatures. Boiling's got to be one critical point, one boiling point temperature. Okay, I've got to move on. That's it. Hopefully that helped you guys. Again, any phase change is a physical change. As we go from solid to liquid to gas, you gain thermal energy. And as you go from gas to liquid to solid, wait for tomorrow if your teacher is not here. You lose thermal energy or it gets transferred out. Okay? This is pretty much a gist of 2-2. And thanks for checking in. All right, now I'm going to film next door. Where are we going? It's funny, as in chapter 1, you just mentioned that the molecules, we talk about their arrangement, solids, definite shape, definite volume. Liquids take the shape of the container with a volume. Gases, no definite shape, no volume. Dude, this comes back again. This material builds. Okay? We just talked about density, mass, and volume. Dr. Phillips even mentioned liquid displacement. Okay, something from chapter 1 helps you understand chapter 2. So all this stuff builds. All right? Okay.
All right.
Good call, Miss Cameron. Look at you, like, building on prior knowledge.
Yeah, we've got to remember
That is
that.
one awesome pair of sunglasses.
Isn't that great? It's from Mrs. Kasevich.
Look at that. Now, hold on a second.
And how about, did you get my light warmers here?
Oh, gosh. Go ahead, Mr. Savage. Dude, they are bright.
They're
Whoa,
bright.
man. Look at
They're
this.
bright.
But you're still the same person, right?
Still the same person,
Cool.
even with leg warmers on.
There you go. There you go.
Very good.
Dude, we're becoming celebrities here. This is scary. All right, here we go.
All right.
Uh-oh.
So,
Hold on, let me zoom in here, because again, I don't know what I'm doing with this camera. Here we go.
here. All right.
feather.
So, Mr. Parcia talked about a physical change.
Let's get physical. Oh, never mind. Go ahead.
That's what started this whole thing.
Exactly, I know.
Olivia Newton-John. Okay.
What a
I'm
name.
going to talk a little bit about chemical changes. In
Oh.
chemical change, we get new substances, completely new substances. But we use the same atoms. They just get rearranged.
Oh, yes.
So on the board here, I have a chemical equation. And we
Look
have
at that.
symbols.
Miss Cameron, it looks so scary. It looks so science-like.
It does.
But is it hard?
No. We're
You
gonna
sure?
break it down.
Okay. Oh,
We're
good.
breaking this
Okay.
So here we have a symbol, a capital letter and a lowercase letter.
Oh, yes.
That represents one element. Ca, we would look on the periodic table, and that represents calcium. We come over here, don't worry about the numbers. We have H2O, we're familiar with that. Hydrogen, 2 of them, and and oxygen to make a water molecule.
Perfect. Look at that.
All right,
Don't worry about
yeah.
those numbers yet, right?
We're
There's a
not worried
big
about
number there.
numbers.
Okay.
Alright, so I'm going to represent my one calcium atom. I'm going to put a little square up here.
Ooh. Oh, look at you.
Look at that.
You love your shapes. Looking back over here.
Yeah, I do.
I love that stuff. Good visual stuff.
Alright.
I'm the loud one. You're the visual one. This is awesome.
Our hydrogen, this number here is called a coefficient. We'll
Oh,
learn more about
big bad
this
coefficient.
at the end of the year chemistry.
Oh.
But when we see this tells us I have 4 hydrogens. Can you see that? Am I
Oh, yeah, dude. This is awesome.
Make 4 dots.
Awesome.
Okay.
Dude, I
And
love
then the
this.
oxygen, again, that coefficient tells us that I have 2 oxygen atoms as well.
I'm stealing this idea from my class. Go ahead.
Really, it's telling us there's 2 molecules of water, but we just want to see how we're going to start with the same atoms. We're going to end with the same atoms over here.
Look at this.
When this reaction takes place
Where am I going?
in real life,
Hold on.
this
Oh, you
is
put the
end.
indicator in there.
I did.
Look at that, you rebel. That looks psychedelic.
That calcium
Awesome.
hydroxide's at the
Look at
bottom
that.
there. But let's take a look. This is calcium hydroxide, and it has completely different properties.
But-
this was silver. This was white.
Oh, the colors,
The
yeah.
colors were different.
But there's calcium in there and stuff.
I know, everybody thinks calcium's white because of our teeth and our bones, and we drink milk with calcium.
Mine are yellow because I drink a lot of coffee. Go ahead. And I'm too cheap to get them whitened. Go ahead.
But when it goes through a change, it gets new properties. But look, it's still one calcium atom.
Dude, I love this demo.
When we look here,
I'm doing it.
this 2 tells me I have 2 oxygens.
So
Oh,
like
that
distributes.
matches.
Oh yeah.
Can you see it? I kind of ran out
Dude,
of
this
room.
is awesome. No, you're
We're
good.
using the chalkboard.
Yeah, we
not
don't.
the Smart.
No, that's 2010. Back to the Future. Oh yeah. I mean, no, that's 1984. Michael J. Fox, right? Go
Yeah,
ahead.
very good.
Oh gosh.
So this tells us we have
Oh my.
2 hydrogens and 2 hydrogens.
We've stooped to a new low here. Go ahead.
So on this side, we call these our reactants.
Participants in a reaction.
Are ingredients.
Oh yeah.
Like a bacon cake.
Yeah.
This is the product. That's what we end with. But notice, I still have 1 red dot
Absolutely.
on each side of that arrow.
Absolutely.
I have 4 here, 4 blue dots.
Perfect.
I have 2 yellow, 2 yellow.
Perfect.
I took these pieces, bonds were broken, and they were put together in a different format.
So can I ask something else now?
Yeah.
Because I really like the fact you were talking about building from like chapter 1.
Right.
Did you just say the word bond like together and stuff?
Yeah. Do I get to sing?
If you want, it's all, hold on. So again, something from chapter 1 builds on into chapter 2. If you want to sing that song, that's quite all right.
That's all right. So,
Bond together, atoms, molecules.
here's the other thing. Law of conservation of mass.
I fought the law. Oh, I better stop. I'm not giving that away. Go ahead.
So even if I took the mass of all of these little teeny tiny atoms and add them up, it would equal on this side to this side of the equation. And when I talk about sides, I mean on either side of our arrow.
So the
That's
arrow,
where the reaction takes place.
so the arrow means like yields, like it makes, like you start off the calcium in the water,
Right.
and excuse me, water, whatever you call it, and all of a sudden it makes or yields. That's what the arrow thingy means, and it makes like final products and stuff, calcium hydroxide and hydrogen gas. Oh, that's awesome.
And then these have completely different properties than what we started with.
So the pieces are the same, they just get rearranged. So nothing was created or destroyed. We didn't add a silver, element on the right side, or lose a silver from the left to the right. It's all can be accounted for.
My classes, we've even played around with Connects. I don't think that's an 80s thing. We would
Legos?
Legos. Okay.
For me, I was a little kid back then, Duplos, the baby Legos.
Oh yeah.
That's right.
That's good. So we used even these pieces to see how we could do just that, but we won't give all that away.
No.
So
We'll be good.
kids can remember.
Awesome. Cool.
Good?
That is awesome. So colorful, so perfect, and so old school. No whiteboard! Oh, 1984. Look at that. All right, cool.
1984.
What else? Do we have anything else to do?
10th grade, 1984.
Look at that periodic table. Where are we going now? Do we have more? Are we done?
Mr. Back?
We got the
Are we doing
back.
Chemical and physical changes? Or-
Oh,
I got 2 minutes to do chemical and physical changes. We're live. You want to do it?
go for it.
You want to go for it?
Savage.
Do we go over to Miss Antel's room, or do you want to do it here?
Let's go over to Mrs. Antel's.
Okay, here we go. Let's do it. We're live and impromptu. Here we go. Let's do it. I got 2 minutes.
2 minutes. 2 minutes.
Wait a minute. Last week was being nice. Look how nice this is. No pun intended. Being nice, beryllium, nitrogen, iodine, cesium. What is this over here? Think? Oh yeah, thorium, iodine, nitrogen, potassium. Potassium starts with K? Oh yeah. Oh, I got sayings for all these. Hey, Miss Camilleri, when you're giving a test on this, you better cover these up. All right, but that's awesome. Look at that. Look how nice this room is. All right, here we go. Here we go. Uh-oh. Can I come in?
Well, we're just thinking, I think we're good.
We're good?
Yeah. Can you think of anything
Whoa,
else
Miss
we need to
Kasevich.
do?
What is that? Oh, is that the mullet wig?
This is the mullet
I thought that
wig.
was like a tarantula or something. Look at that. That is awesome. So again, physical change looks different but stays the same. Chemical change, it looks different because it is different. So we're... Go ahead.
Different, but,
But
I'm
you're
still the same.
You're still the same.
Not a new person.
Exactly. Look at that. Dude, that is awesome. Perfect. So we'll hit the rest of the material in class, chemical changes, but I think we got a lot today. Thank you for watching. And that is it. Hope you had a gnarly time watching this movie. There we go. All right, I'm going to turn that off. Have a good day.